All right. Are you seeing the slides? Okay. So yeah, my name is Yumi Choi. Here are some today's agenda for today's assembly. So we'll start with a couple of announcements, and then start my presentation on the portal tutorial to demonstrate how to do the DP 0.3 phase curve fit analysis. So the RSP account first. If you have any problems with your RSP account that has been recently created, please let us know in the chat, and the CST member could help you with that. And as many of you know, the Rubin Community Workshop 2024 is coming in July, this time at Slack. And the call for the session proposals and the contributed abstracts has been out. And today is the, tomorrow is the deadline for the early bird deadline. So if you're interested in, please submit your proposals for the session ideas and the abstracts as soon as possible. And registration is also open now. So please keep that in mind that there is a 250 cap in person participation. So please register as soon as possible. And from June 12th to 17th to 12th, 21st, except for the Juneteenth holiday, we'll have Rubin Data Academy 2024, which was formerly DP0 virtual summer school. So there will be a series of presentations, hands-on tutorials, and co-working sessions. So students are especially welcome, but no previous experience on RSP or preparations are needed. And please stay tuned for the further details. And there will be the first LSST at Latin America is coming up in June. And the LSST at Europe 6 is happening in September. And then another exciting news is that the Rubin's LSST camera is complete. So please check out the Slack press release, which came out yesterday. And also with that, Rubin is hiring, and there's multiple positions openings for positions. So please check that out too. And here are the future schedule for the Rubin Science Assembly. We have tutorial sessions every 2 weeks, and then drop-in sessions in alternating weeks. So next week at this time, we will have a drop-in office hour for the Q&A sessions with Rubin staff, or you can come and co-work with other delegates. And 2 weeks from today, Aaron Meisner will present notebook tutorials on DP 0.2 custom co-eds. Okay, so I think Andreas will make an short announcement on the portal aspect of the RSP usability test. Take it away.
Yeah, thank you, Yumi. My name is Andres Plazas Malagon. I'm part of the community science team. I work for Slack National Lab. And I wanted to advertise this usability test of the portal aspect of the RSP. We would like to encourage you as delegates to help us give us feedback to understand how you interact with the portal and how you can do, if you can do the science that you want to do with LSST using the portal. So you just need to have an account, an RSP account at datalsst.cloud. If you don't have one, please get in touch with us. But if you're delegates, you probably already have one. And you only need to go to this website that is listed here, where you're going to find a series of exercises. There are 6 exercises where you can pick with different levels of experience. And once you have completed one exercise, each one should take about 20-25 minutes or maybe less. Once you have completed each exercise, please go to this Google form. That's the second link in the slide to give us feedback. You're going to find out just a few questions, and then you're going to have the chance to just tell us what you thought of the exercise and the portal in general. I'm going to be sending a message to the DP0 delegates and community just for reference with this information. And also we might keep doing this in the future. As you know, the portal's still evolving and in development, so we might ask you to participate again in this exercise. Thank you so much. If you have any questions, let us know. My email address is right there. Thank you.
Thank you. Okay, so let's get started the portal tutorial. And this is the portal tutorial we're going to go through together today. I'm going to copy the link to the portal tutorial to the chat. And that's called a phase curve fit analysis. And it is basically the same demonstration shown in the notebook tutorial 4A here, but focus on the main belt asteroids. And there is another notebook tutorial 4B, TP 0.34B, where we presented how to fit phase curves for solar system object, which cannot be done in the portal because of the limitations in the portal aspect. So if you are interested in phase curve fitting itself, then please check out notebook tutorial 4B as well, or the recordings of the assemblies back in, I think, in November last year. Okay, so maybe before jumping into the steps in the portal tutorial, let's talk about briefly a few key concepts about the phase curve, which is helpful to understand the process we're going to go through today. But the disclaimer that I'm not a solar system expert at all. Anyway, so this diagram will helpful. I think here's the sun and here's the earth, and there's a solar system object. And as solar system objects move around, orbit about the sun, they continuously change their positions and the brightness, meaning their positional and the photometric measurements from each between Rubin images change over time as well. So by using these time series data for solar system object, we can measure their intrinsic properties and also reconstruct their orbital parameters. And one of the intrinsic properties of the solar system object is the absolute magnitude of an object. And here, this alpha is an angle between the two lines. One line between the object and then Earth, and then the other one between the object and the sun. So this is called solar phase angle, or phase angle in short. And then when the sun, Earth, and object align like this at a phase angle of 0, and the object gets fully illuminated and becomes the brightest. So the magnitude at 0 phase angle, and as if the object is at 1 AU, both from the Earth and the sun, that brightness we called absolute magnitude by definition of the solar system object. And that's what we want to know. But apparent brightness that are observing is not just here, not just a function of the phase angle alpha, but also a function of relative positions between between the sun and the object, and then between the object and us. So remove this distance dependence on the apparent magnitude. The reduced magnitude concept of the reduced magnitude was introduced. So here it's called H alpha. So it's only a function of phase angle of alpha. And here M is the apparent magnitude, and then we correct for the relative distance between the object and Earth and the object and sun. So dt here is the topocentric distance, which is the distance between the Earth and the object. and then dh is the heliocentric distance, the distance between the sun and the object. So by subtracting by subtracting 5 times log 10 of dt times dh from the apparent magnitude we observe, we get the reduced magnitude, which is a distance dependence free. And this reduced magnitude, so basically it's renormalized as if the object is at both 1 AU, both from the sun and the earth. Okay. And then, so once we do that, and then the phase curve is a demonstration of the reduced magnitude we just described as a function of phase angle. So these are the data points, and then these called phase curve. And by fitting these data points to a functional form, we get what is the absolute magnitude at phase angle of 0. So that would be the absolute magnitude we want to measure from this phase curve data, and by fitting the data to the functional form. Okay, and in DP 0.3, the functional forms to fit the data, the phase curve, there are various functional forms, but in the DP 0.3, we use 2 mainly. The first one is the HG model. So it has the H, the absolute magnitude, and the slope parameter G. And then these H and G parameters are stored in the MPC orb data as an input truth value to simulate the phase curves in DP 0.3. And note that in the DP 0.3 simulation, they only use a single value for the slope parameter G, which was a constant value of 0.15 in V magnitude, in V band. And then another functional form or the model is the HG12 model, which are the Rubin pipeline is using to constrain the phase curve. And this model has also 2 parameters, H, the absolute magnitude, and the G12 parameter, which is kind of slope parameters, but it's not exactly the same as G parameter for the HG model. But this HG12 model is known to very effective and reliable for the case when the phase angle sampling is not optimal, which is close to be the real observation. So we have these 2 models in the DP 0.3. Okay. And I think these are the key concepts we need to understand this the phase curve tutorial. But do you have any questions on this? Okay, if not, then we can go through each step, right? So first, we go to the data.lsst.cloud and RSP and log into the RSP now. Okay, so I'm logged on using my org ID. Working. Okay, so now I'm in the RSP. We go to the portal. And the first thing is, so this portal tutorial will focus on the main belt asteroid. So we'll start with retrieving some data for the main belt asteroid and using this query. So I copy this ADAQL query from the tutorial. And here, first we need to go to the tab service on the right, and then by default, hide is selected, but we click the show Then there is the drop-down menu, and we can select the LSSTDP 0.3 SSO. So here are two versions of the schema, the simulation, one for the, as we observe, at after a year of the LSST observation, and at the end of 10-year observations of the LSST. So we're going to use the 10-year tables, the simulation, and then there are 4 tables that, and then the SS object table is for the unique solar system object table, and then MPC orb as a table for the orbital parameters, and there's a one-to-one relationship between the MPC orb and then the SS object tables. And then the next one we are going to use also is the DIA source, which is the table for the measurements for the from the difference images. So this is basically from the single visit images, but the making difference images, and we make measurements. And then the SS source table is the single visit measurement table. So there is a one-to-one relationship between DIA source and SS source tables. So here, but then rather than using like constraints and then retrieve the data, we're gonna go to the edit ADQL page, and I'm gonna paste the query I just copied from the portal tutorial. So basically here, I'm gonna retrieve main belt asteroid, which has the semi-major axis A is between 2 AU and 3.25 AU, and then perihelion distance greater than 1.666, and then the total number of observations are greater than 100. And we're gonna retrieve the H, the absolute parameter, absolute magnitude, and then G12, the slope parameter, and their errors in each filter, GRIZ, and the number of data points in each filter as well. And here we just limit the SS object ID range just to reduce the query execution time. So this is kind of arbitrarily selection. But then I'm going to retrieve 100,000 main belt asteroids. So I changed the low limit to 100,000 and click search. Okay, takes some time. And this is why we set the range of the SS object ID, which helped to return the query result relatively quickly. So we got the tables of 100,000 MBAs, the main belt asteroids, and here cannot display request data is perfect. It's just expected. And now we want to just make sure that we got right semi-major axis distribution for the MBAs we retrieved. So here we click the 2 gear icons here to pop up the plot parameters, and click the add new chart. And we're gonna make a histogram of the semi-major axis distribution. So, but the semi-major axis is not recorded in the table by default. So we need to use the perihelion distance divided by 1 minus eccentricity of the object. So I'm just making the number of bins 200 and then make this. Okay, we can click and to close this panel, and here it shows the the distribution of the MBAs. And as we can see, it ranges from 2 AU to 3.25 AU, so which is good. And we can see multiple peaks and gaps. And these gaps are known Quirkwood gaps arising from the resonances between the asteroids and the Jupiter's orbital period. So I think we got good MBAs with the total number of observation greater than 100. Okay, so then what we want to do next is that select one really well observed MBA and then plot its phase curve. So to select a well observed MBA, I'm going to put a constraint under the num-ops column saying, okay, I want MBAs with the number of observation greater than 2000. So like this, and then hit return key. And then we got like 23 MBAs with total number of observation greater than 2000, which is good. And you can pick a random whatever MBAs you like from here. But if you just hover over the subject ID, and you can see a triple dot box here. And then if we click the same object in the tutorial and click it, and then there's two options to copy this object ID to clipboard or view as a plain text. So we're gonna copy this in the clipboard and go back to the RSP tab search to retrieve all the individual observations of this particular object. So that will be coming from the DIA source and the SS source tables. So here we go back to the ADQL query page, and then we can copy the ADQL query in the portal and paste here. So for that particular the MBAs with one of the the MBAs with an ops greater than 2000, we're gonna retrieve the magnitude and magnitude error, and then band information like GRIZ and phase angle and the topocentric distance and heliocentric distance information from the DIA source table. So here we hit the search button, and you can see this is all the measurements. So there are 2032 observations for this one particular object across 4-band GRIZ. Recall that the TP0.3 doesn't have U or Y simulations. So let's focus on just G-band. So if you want to select the G-band measurement, you can type equals G and probably in the quotation mark under the band column and hit the return key. And that gives you only the G-band measurements for this particular object. So now we plot the phase curve for this this object. So axis should be the phase angle, and then y-axis should be the reduced magnitude, not just the apparent magnitude. So we need the distance correction here. So 5 times log topocentric distance, right? And times heliocentric. Oh. Times heliocentric distance. Okay, and then so this is going to be the reduced magnitude, and we want to plot the error bars on that reduced magnitude as well using the mag error column. And then trace options could be stay default, but we wanna, so here the X label will be phase angle, and like degree, and Y label will be reduced mag, and we want the Y-axis to be reversed. So the brighter magnitude could be on top and then fainter can go bottom. And I think that's it. Right. No. Okay, apply. All right. Oh, now can I? Okay. It shouldn't look like this. Topocentric times heliocentric distance. Oh, should be right. Do you see any mistake that I made?
I think it's log 10, not log.
Okay, here. Oh, sorry. Okay, and then Y reversed. Okay, so we don't have the y-axis label, but yes, the phase curve looks great. Oh, maybe we should the error right here. Error, and it can be like reduced mag. Okay, Y. All right, it looks great. So this is the G-band phase curve for this particular object. And if you wanna look at phase curve in other filter, you can change G to like I, and it will change the plot for you. And if we look at the G band, then the phase curve less sampled compared to the G or I, but then also the error bars on the smaller phase angle is larger compared to the G band, right? So, and the absolute magnitude we're talking about is the magnitude at the phase angle of 0. So, as the magnitude, the brightness gets brighter, the error bars are getting smaller. But in G band, Z band has a larger error bars that even at the smaller phase angle compared to the G band or I band phase curve. So this is the phase curve for one particular object, and you can try for other object as well. All right, so now we explore the phase curve data products in the DP0.3 catalogs in general. So we retrieved H and the G12 parameters and their errors in each filter for 100,000 sources, right? So we can make the and then if you want to remove this constraint, so you want to go back to the 110 data table, then you can just easily simply just remove this and then hit the return key, or do this and then you can just click this icon on the right top like this. So we back to the 100,000 object table now. And then we're gonna make a new plot to see the distribution, 2D distribution of the phase curve parameters H and G12. So we're gonna add new chart, and that's not the histogram, but heat map. And then x-axis will be the G-band absolute magnitude, and then y-axis will be the G-band G12 parameter. And then number of X bins could be like 100, 100, and then the chart option, we can say X label as GH, and then Y label as GG12, and then set the y-axis range from minus 0.1 to 2. Okay. All right, so we got this one, and then we can remove this histogram. And then we can repeat the same process for the other filter to make a comparison. Okay, R12, 1, 2, and 100, 100, and Y, the same range to make a one-to-one comparison easily. Okay, so give it another one, I, and this is the I bands now. 100, 100, and then, okay, if we make one more, then the plot ratio will be 3D, so we can keep going. So, and now Z band, 100, 100. One, two. Okay, so this is the slope parameter G12, and then the absolute magnitude comparison in GRIZ bands. As I mentioned at the beginning, for the DP0.3 phase curve simulations, the input truth value using the HG model, the G was set to constant value of 0.15 in V band, visual band. So the numbers doesn't match exactly, but as you can see in all bands, the G12 values are pretty much constant. The medium values are pretty much constant. But then the scatters are getting broader at the fainter magnitude, which is kind of expected. So this is the distribution of the DP0.3 MBA base curve properties, like general properties in terms of like G12 and then H parameters. Any questions? Oh, here, Greg mentioned that you can limit the display to just the plots by clicking on the double diagonal arrows icon on the upper. Oh, this one, I think. Okay, thanks. Right, if there's no, error bars. Let's see, chart option, min and max.
I don't think we have that feature. So Bob asked about whether the color bars on all four plots could be made to have the same range. That's an excellent suggestion, and I'm taking a note of it right now.
Thank you.
I have one other suggestion. Sorry. Can we make the XY boxes bigger so that we can actually see when we're putting in a long equation that we can enter it easier?
Just make those expression entry boxes wider. Yeah, that's a
yeah, that would be fabulous.
Yeah, because when we calculate the reduced magnitude, it was kind of hidden, the later part. Yeah, I think in the histogram plotting option, we can set the min and max for the y axis, so we can have the same, like the height, but yeah. same scale color bar would be really helpful.
Yeah, we're taking note of that. That's an obvious one. This should just have a Z range for
Yes.
heat maps. Yep.
Great. Thank you. All right. So these are the distribution of the phase curve parameters, but then the phase curve parameter fitting might be depending on the number of total observations. You know, the number of observations. If you have more observations, you might have a better constraint on the phase curve, or if your objects are closer to you, so which means it's brighter on the sky, that probably you have a better photometric measurements, and then that could give you a better fit. So let's make a plot to see that if that's really the case. So now click all these plots, but leave one. And then we can add new chart. So now we're going to look at the phase curve parameter errors, uncertainties versus the number of observation and versus the perihelion distance. So we're going to make a heat map as well. Maybe we can just use this modify, not new chart. Here, let's do like I band H error. Right. So this is the absolute magnitude errors in I band, and sorry, this should be the number of observations, the total number of observation versus the I band H error. And we can keep this the same, and maybe we can set the white limits here to be 0 to 0.05. Okay. Right. So we have I band H error versus the number of observation here. And then we can add new plots. Add new plot and heat map, and now the x-axis is the perihelion distance and the error H, I band H error. Okay, so we can do 100. Okay, and then another new plot, heat map, but now I band the slope parameter error. This should be on the y-axis, and the x-axis is the number of observation. Wait, forgot to set this y maximum. So we have that. Okay, then I can modify this and setting the y mean and y max as well. Okay, and then one more new. This time, Q, and then I band G1 to error. 100. Y range again, forgot. Okay. Y. Oh, sorry about that. This should be 0.0, not 0.05, but 0.5. Okay, this is good. And then this one also. Right. So just try to keep the same y-axis range to make a quick comparison. And so what we can see is that the errors in the phase curve width parameter, the absolute magnitude, and the G12 slope parameter, the uncertainties decrease as you have more observations, indicating that as the LSST observation keep going, then we'll get a better constraint in the phase curves of the solar system object. And as a function of perihelion distance, probably there's a little bit of trend. If your object is slightly closer, then you will have a slightly smaller uncertainties on both parameters, but probably not significant as much as the number of observation. Okay, and this is the here the number of observation is like total number of observation across the GRIZ band, but the phase curve could be different, and then the quality in different filters could be also different sampling. So now what we can look at is the number of observation in each filter. So let's look at the distribution of that. Here we can add new histogram, and then this should be the G band and data. So this is just showing the number of observation in G band, not the O bands. Then we can do like number of bins, 100, and then I'm gonna set the maximum to 1300, and nothing for the charts, but then log scale. We can select the log scale for the y-axis. Okay, let's try this one. Okay, now click the old plots. All right, so we have the G-band observation, the number of data histogram here, and then we're gonna add different filters and overplot those histograms on the same panel. So overplot new trace, histogram, and column are and data now. And same number of bins and same min max. Okay, and so now you can see new things under the trace option. So you can, so this is basically labeling each histogram. So you can say, okay, this is the GR band and data. And data, okay. And the other things can be stay the same. Okay, so now you can see the green histograms labeled as R and data. And we wanna label for the G band. So we can go back to the plot parameter. Now you can say, select the R and data or trace one, which is the G band plot we made first. So now you can go back and then add and data. So Greg, maybe another suggestion is if we can put a name, trace option name thing when you make the first histogram, that might be also helpful. We don't need to go back.
Yeah, that makes sense.
Yep. Right. So now you can see the G band is also labeled not trace 0 anymore. And then we overplot another one. To open again and overplot new trace. Now GRI and data. Same. Okay, and then R and data. Okay. So we got another one and one more for the D and data. D and data. Okay, so we got 4 histograms for the number of observations in each filter. Oh, which one is the? Okay, I think this one is the I. But if you click the legend here, you can hide, and then calling back. So as you can see, G band has less data points, and then Z band has less points, but R and I has more observations. So probably we'll have a better constraints in R and I bands, especially for the phase curve fitting, because we have more data points in these filters. Okay, so lastly, we can check if that is really the case, like G band, Z band versus the I band. The phase curve fit parameters are having smaller uncertainties. We can check that by adding a new chart. Now we can make a heat map, and x-axis is the I band, absolute magnitude uncertainty, and the y band, axis is the Z band, absolute magnitude errors. Right. And then number of bins, we can do like 100, and click this. And if we make the XY ratios set to 1 and stretch to width, then probably we can get a square looking plots. But maybe we can set X and Y.
I think if you do that expand thing, the double diagonal arrow, and you just work in that mode, you'll have to close the dialog first, but you'll just have a lot more room for what you're doing here.
Okay, that's correct. Okay, maybe I can set the my minimum to okay. Right, so yeah, so on the x-axis, the I band absolute magnitude error is much smaller than the Z band absolute magnitude measurement. So there are other factors, of course, but one explained could be a different number of data points in different filters. So, we have more data points in I compared to the Z. So that's, I think, showing what's the impact of number of data points on the phase curve constraining. I think this is the end of the Portal tutorial. Just demonstrate how you can explore different phase curve fit parameters provided in the DP0.3 simulation. So yeah, if there's any questions, please let me know.
And thank you very much. It's really great to see it being used and to get, concrete feedback. That's very helpful to us.
Okay, thanks. Thanks for supporting this functionality.
There's just one other little thing I wanted to encourage you to try for the viewers to see before we stop. I noticed when you were making more plots, you often removed the previous ones because it was getting crowded. There is this single plot mode, So if you, yeah, exactly. So you can focus on one plot at a time. I think you need to like zoom in this case, but I think this is maybe we've run across a small bug there that has to do with the possibly the aspect ratio constraint. But in any case, you can then there's the arrow at the top that says plot 0.
Yep.
You can use that one to switch to your other plot.
I see.
And you can cycle through all the plots that you have in a session by doing that. So you can
I see.
choose being in
good.
child mode, or you can choose being in one plot at a time mode.
Yeah, I see. So that doesn't restrict to the number of panels at the same time. So we can just
Yeah, I mean,
browsing through.
you know, all the plots that are in existence they're all live, of course. So they're eventually probably you might want to start cleaning up, but you can have a large number of plots in a session.
Okay, good to know. Thank you. Okay, any other questions? If not, I think we can get you like 7 minutes back. And next week, we'll have the drop-in session. So if you have any questions, then come to the same Zoom room. And yeah, the Rubin steps will be here. And then you can work with other delegates as well. Right. Then I'm gonna